theory has given information to many new theories. Let's add one thing for the young audience. The work of Waldschmidt is not only limited to number theory. It's a constant which is after Waldschmidt and commutative algebra, which is known as Waldschmidt constant, and which is linked with one of the central problems in commutative algebra, which I came across in the year 2015. And up till now, that Waldschmidt constant has attracted a lot of research work. Many have working on Waldschmidt, but today he will be talking about transcendental number. It's name analytic and algebraic geometry. So over to you, Waldschmidt. Good to welcome to Labs.
Thank you very much for this invitation. Well, it's an introduction to this content that I am going to do right now, but in rather elementary terms. I first of all wish to thank Professor Hilbert for his invitation to give this lecture. As several of you know, it's not my visit to Pakistan, nor to Lahore, nor to Lens. I came at least before in Lens, and I came 9 times in Pakistan, including 8 times in Lahore. And I am very glad to have this opportunity of speaking on the non-convex similar theories, the opportunity and and consider the finite set of considered plane, and we ask what is the smallest degree of the polynomial which vanishes on these points. The smallest degree of the polynomial is the same as the degree of the hypersurface which contains these points. But what is important is that we have some multiplicity. So you start with this problem, and yes, multiplicity is highlighted. I love the word, and I will explain that it's connected with the conjectures of Nagata. One of them is on transcendental theory, and the other is related with the Hilbert 14 problem. So this is the abstract of my book. So I start with, I'm sorry, can you come back? Can you come back? Because no. Okay. I start with classical result from the geometry, Euclidean or projective geometry, which is that if you have 5 points in a plane, there is a conic which passes through these 5 points. It's a result which was proved probably for the first time by Blaise Pascal, so we often say that it's a result due to Blaise Pascal. And you may know the program which is GeoGebra. I use it for some pictures that we will see. It's a very simple program, and I am not so clever on using computers, and it enables one to draw some pictures which are very simple pictures. And this logo of GeoGebra is an ellipse which contains 5 points. So this is the theorem of Pascal. So in the Euclidean or projective geometry, if you have 2 points, it determines a line. If you have 5 points, it determines a conic. 9 points, it's a cubic. 14 points, it's a quartic, and it continues like this. So this is the start of my investigation. And I explained that the line is a linear equation with 3 coefficients because we are in 2 variables. And therefore, if we have 2 coefficients, we can solve 2 linear equations which are homogeneous because it's equality. So this is why we can, if we have 2 equations, we can find a line which passes through the 2 points. For the conic, the number of coefficients 6, which means that we can solve 5 equations. So if we have 5 points, we can always find a conic which passes through this point. And for a cubic, you count the number of coefficients, you find that then it is the 6 plus 4, the 4 which are below, and so you can solve 9 equations. So this is just the linear algebra. Now, I will look especially at the theorem of Pascal when you have 5 points. When at 5 points you have conic, and you can ask, is this conic unique? And also, is this conic degenerate? The degenerate conic is just 2 lines, the union of 2 lines. You have 2 linear factors, and so 2 lines is considered as a degenerate conic. When is such a conic passing with 5 points degenerate? It means that on one line you have 2 points, and on the other line you have 2 points. But if you intersect the line with the conic, the line at degree 1, the conic at degree 2, number of intersection points is 2, unless it is degenerate. And so if you have 3 points, it means that you have the union of 2 lines. And if you are in this situation, again, there is unicity, because on this line you have 3 points, so you cannot have another degenerate conic. You have not unicity if and only if you have 4 points on one line, and the other point, which is outside, and then you see that this line which is here can choose it. So there is no unicity. This is the only case. Now, if you like to write down the equation of the conic, it's not difficult. You write the coordinates of the 5 points with x1, y1, x2, y2, x2, x5, y5, and you can solve the system just by writing this determinant. And this determinant is the full number of degree 2 with the coefficients that you can write down. By the way, the geometric picture gives you some information which is not obvious from this. When I said that there is unicity, that it is degenerate, it's very easy geometrically, but if you look at the determinant, there is a question, yes? By unicity, or when you have 5 points, there is one conic which passes through these 5 points, and you ask, is there another conic? Is the conic which passes through the 5 points unique? And my answer, which I gave just before, is that this conic is unique unless there are 4 of the points on one line, and the fifth one is here, and this line which is here, you can choose it, and so here there is no unicity, and this is the only case that there is no unity. So you may have learned that when you have 3 points, it determines a circle. But what is the connection between the 3-point theorem and the 5-point theorem that I mentioned before, of Pascal? There is a strong connection, because in Euclidean geometry, a circle is conic which passes to 2 cyclic points. So you have to take complex values, and the final term is x squared plus y squared, and you have x equals plus or minus I, which are the 2 cyclic points. But for that, you have to take the package projective plane. So it's a little bit more general, but the theorem about 3 points is a special case of the theorem of Pascal. You should not be surprised that the 3 points are sufficient, because the 2 other points are hidden. They are hidden because they are at infinity in the complex projective plane. So they are really very well hidden, but we found them. We can say more about the conic. We can ask, is it an ellipse, a parabola, or hyperbola? And Möbius told this. Okay, so it's Möbius, and Möbius. And he put the following result. You take 4 of the points. You have 5 points, you take 4 of them. You have the complex quadrilateral. You have 2 parabolas which goes to this quadrilateral. And you look at the 2 parabolas. If the 5th point is in one of the parabola, you have a parabola which contains 5 points. If it is not of the parabola, it can be inside both parabola, can be outside both parabola. Those cases the conic is hyperbola. And the other case is that the 5th point is inside the 2 parabolas or outside the parabola. In this case, it's So we do, I think we not use that, but good to know that we have more information. Let me come back to this sequence of numbers, which was 2, 5, 9. They come as follows. If you count the number of coefficients of polynomial between two variables, you find that it is equal to 2 equals 1 over just a missing counting process. And so if you have p equal 1, 2, 3, 4, equal 2 over 2, it's 3, 6, 10, 5. And if you want to find the point which satisfies its polynomial, you can solve the linear system provided that you have one less than equal to over 2. So these numbers which you have 2, 5, 9, 14, they are just the binomial coefficient 32 minus 1. So there is no mystery on the sequence of numbers. And now I will be interested, when you have a finite set of points, to look at the smallest degree of a hypersurface which goes through this point. Or if you prefer, the minimum degree of a polynomial which vanishes from S. From linear algebra, what I told you is that if the number of S is less than equal to 2, then this degree, the minimum degree, is bounded by Z. But I will not be happy with 1. I want to have a multiplicity. So for t greater than or equal to 1, I do not by omega t of S the minimum degree of the polynomial vanishing on S with multiplicity at least t. So now, if we want to use the linear algebra, we have to count how many conditions we have. And we have to take the derivatives of p at the point xy for all xy within S. And the derivatives are tau1 with respect to x, tau2 with respect to y, and the sum has to be less than. How many conditions do we have? It is the binomial coefficient 2 plus 1 p. So the condition is that if t is sufficiently large, and this is exactly what we need, then omega t of S is less than d, the reasonable number of omega at most d, satisfying all these conditions. This is just linear algebra. This function omega t of S for a finite subset of S, omega t, is subordinate. Because if you have a polynomial which vanishes at order t1 and another which vanishes at order t2, you take the product, the degree will be the sum of the degrees, and the multiplicity will add, so it will be omega t1. There is a classical result which is duplicated, which says that if we have a subadditive sequence, then the limit of omega t over t exists and is exactly the if, the smallest value, if you like, of omega t over t. So the limit exists. I denote it by capital omega of S. This is the limit of 1 over t omega t of S. And the theorem which I want to explain, that omega of S is less than omega t over t, given by that. But omega of S is not 0. And this is something which is not at all obvious. This limit is positive. And it is at least omega t of S plus 1. And I will explain where this bound comes from. So this is the main constant which I want to investigate. Let me take some special example with S, which is a set with not too many elements. I take S which has 1 or 2 elements. We know that a line is defined by 2 points. If I want to have a multiplicity, I just take the line with the power t. So polynomial linear polynomial with the power t. So this is quite easy. Omega t of S is t. The quotient is 1. Okay. And so there is no mystery for that, either for S equal 1 or S equal 2. So capital omega of S in this case is just 1. If you take a set with 3 points, then it becomes interesting because if you want a polynomial which passes to all those points, if the 3 points are not on the straight line, you need a polynomial 2 equally. that if you want to have a multiplicity, it's sufficient to take the product of the three lines, which has degree 3, there are 3 points. And so you have a polynomial 3, you can write it down with t, which has the property that at the 3 points, the multiplicity is at least 2, which means that omega 2 of S is equal to 3. It's easy that not to it is 3. In general, if you want to have a multiplicity which is at least 2n minus 1, you take 3n minus 1, this polynomial, you take n times this one, n times this one, and this one, n this one times, and omega 2n is 3. So, in other terms, omega t of S for S, a set of 3 points which are not multiple time, it will be 3t plus 1 over 2 or 3t over 2 for even. And then we can compute the quotient, the limit of omega t over t, but 3 times. So this is the first example of omega of S, which is less than omega 1 of S, omega 1 of S, and which is greater than omega t plus 1 divided by t plus 1. So this number, capital omega of S, is an interesting number, which I want to investigate further. The next example is with 4 points. With 4 points, if you want a polynomial which vanishes with a multiplicity 1, you take 2 lines. 2 can take 2 lines like this and 2 lines like that. And so you see that omega t of S just 2t. You take 2 times the t times 2 lines. So this is omega t of S for the grid, which is the Cartesian product with the 2 elements. It is the same in general if you have the Cartesian product S1 plus S2. If S1 and S2 have 10 elements, then omega t of S is empty. And so the limit of capital omega of S is the square root of the number of elements. So the case of the grid of the Cartesian product is easy, and this is the same for 4 points in general. We have seen the answer when we have 5 points. 5 points lie on the conic, and so omega 1 of S is 2. It's always less than 2 if you have 5 points. If you are on the line, it's 1, but in general, it's always less than 2. And if you take the t power of the quadratic number, which is not your conic, then you will find that omega t of S is bounded by 2t, and therefore capital omega of S is less than 2. So I notice here that omega t of t is less than 2, which is then an conic of S. This bound omega t of t less than 2 of S will come back here in the next example. So this is 5 points. Let me move to 6 points. And this case of 6 points was studied by Nagata. And Nagata made a very clever remark, which is that if you take 6 points general position, which means that the omega t of S is the maximum, so you have this one. What you can do is that for each of the 6 points, you have 5 remaining points, and you have a conic which passes through this point. So you select 1 point H1, and you have a conic which passes through the other point. But you can do the same for S2 and 6. So you have 6 conics, and the degree of the product will be 12. And for each point, 5 of them pass through this point. So the multiplicity will be 5. And so this gives omega t over t, which is 12, which again is less than the square root of 6. 6 is the number of units. You see, here we have 2.4 and 2.44. Okay, this is 6. Next, for 7, Nagata has another construction. And the other construction is the following. You have 7 points in the 6 point. And with 7, you need a cubic which passes through all these points. So the number of coefficients of the cubic is 10. And you have simple zeros. if you just have that passes through the point, there are 7 conditions. But you can get 2 more, because the number of coefficients is 10. And the 2 more is to ask a double zero at one of them. So for each point, you have a cubic which has the multiplicity 1 at all the other points, but at the point that you have chosen, there is a. So if you count, you will say that you have 7 cubic polynomials. The product has degree 21. There are 7 zeros for 8. And so altogether, omega 8t divided by 80 is 21/8. So this is the next example of this constant capital omega, which is 2.625, and again, less than 30%. I will pass rapidly to the next example. The next example is 8 points. Given 8 points in C squared, there is a sextic, so the curve of degree 6, with a double point at 7 of the points and a single point at 1 of them. You check it as follows. The number of coefficients of the sextic polynomial is 28. The number of conditions is 3 times 7 for the double zero and 6 for the triple zero. And you have a polynomial of degree 48. You have 8 zeros for each 2 plus 1, so it's 17 for each point. So omega t of s for t equals 17, omega t is 48, and you have this value. Okay, I will not continue for a long time. I just go for 3 points, and 9 points. 9 points is easy because 9 points you have a cubic. You take the t power of the cubic, and you have omega t of the t, which is 3, which is 12 volts. So the conclusion of this is that for each step with at most 9 points, there is an integer t, so that omega t is less than t squared. I give an example for each of them, and the example, the complicated one, was given by Nagata. And now I come to the conjectures Nagata. Yes. It is in C1. In C1, yeah. After that, I will come to the end. And so, the question of Nagata is that, is it true for the number of points greater than 10? And this is the famous conjecture of Nagata, which is not solved. And I will explain where it comes from. And Nagata proved that if S, the number of elements of S is square, and that is 16, then there is no t, so that we need a t less than 16. So I give you this values of T9 in detail, because if you can solve the case of a number of elements which is 10, then it will be an achievement, because it will be a counterexample to Nagata conjecture. And we do not know, even for 10, whether there exists a t is not clear. You have to understand the problem that we want to have for any set t, any set s, there is a t, so that omega t of the t is less than 2. For some special sets S, for example, this one, which is a nice set, you can look at the polynomial which has a small degree. You have a multiplicity x at each point. You have 10 points, and the degree of the product of the polynomial is 17, and 17 over 6 is less than 3, which is less than the product of 10. So there are some examples where omega t over t is less than this. But we have to prove that the problem, the problem is that there are some sets for which this does not occur, and these sets are called generic, the one for which we don't have maximum. So this is the picture which I explained, and you see that the smaller values that we find for omega t over t are the values which are good. And all of them are less than the square root of s. All these numbers less than or equal. So whether these numbers are the smallest number is something which is not quite clear. I do not know a proof that we cannot do better than 12.5, but we were happy to have a number which is better than 12.3. Yes. Why did Nagata study this problem? He studied this problem because of Hilbert's 14th problem. You may know that Hilbert asked a series of problems in the International Meeting of Mathematicians in Paris in 1900. There were 23 problems, and he called the 40 of them, and the statement is that K be a field and capital K the field of the field of n of the functions of n variable rational fractions over small k. So capital K contains small k, and we look at the K algebra, which is the intersection of the big field and the degree of integers in the n variable. The question is, in this intersection finitely generated as a K? So this was the question of the and Savitsky proved that the answer is yes for n equal 1 and n equal 2. And so after that, people thought, okay, if it's true for two variables, there is a chance that it's true for more than variables. And Nagata gave a counter example in 19. Nagata put on other version of the problem, which we explained, what is called the restricted case, for sufficient to give a counter example to the restricted case. So the achieve the subgroup of the full linear group of the polynomial group in n important ways. We consider the set of elements which are invariant to the G is finitely generated. And there is a good reference for that by Nagata, where the counter example to. And the group of Nagata, which I will explain, rests on a very important lemma, which is the way which Nagata calls the fundamental lemma. And the fundamental lemma is that if you have all 16 independent generic points on the positive plane of a field and a positive integrity, there is no curve of degree 40 which goes to each clearly. If you translate what it means, it exactly means that if you take a set S which is free, which means that the omega of the S maximal, then the omega T of S is greater strictly than 40. That it is greater than or equal to 40 is not so difficult. That it is greater than 40 more difficult. And this is the lecture of Nagata in the International Congress of Mathematicians in 1958. He has a proposition which is a little bit more precise. You take independent generic points and you take a curve of the degree which translates to the three points with multiplicity that is empty R. And the sum of the MI is bounded by D sort of R, provided that R is the square and R is at least 60. Square of S and decimal of. The conjecture, which is the conjecture of Nagata, is that he said it is not known if R greater than 9 is sufficient to ensure the inequality of the multitude. R greater than 9 means that instead of R is a square, we just argue that R is at least 10. We do not assume that R is a square. And so this is the conjecture of Nagata. The reformulation of Nagata's conjecture is if S is the finite generic point of the projective plane, so it means S greater than or equal to 10, then omega T is greater strictly than it's greater. And Nagata proves that it's true. S is a square, and that it is false if S is less than or equal to 9. I was a bit puzzled when I saw that. What happens is 9 to 10. And in fact, not so good for me. What I will do is to define another number which depends only on the number of elements of S, which I call small s. Given a positive integer small s, which will be the number of s, I look at the smallest integer b such that the b plus 2 b plus 1 is greater than s plus 1, which means that if we have a set with capital S, small s element, we know by linear algebra that there is a polynomial. So from the definition of omega t is less than omega prime t. And the relevance of 9 is that given the positive integer s is less than 9 if and only if there exists a t, the omega prime t less than omega prime t. So the example that we have seen, they arise not because of clever constructions with ellipse and the polynomial between 2 and 6, they just arise from linear algebra. The proof is here. I will not give you, it's very elementary, but this number omega prime of s is satisfies this property if and only if s is omega prime. And so, in this case, we can look at what is omega prime of s. So I take the same picture as before, but I replace omega s, omega t by omega prime t. And what you see that the non-position is 5, 12, 8, 21, 17, 48 are exactly the same as for omega t, which means that very likely that what Nagata did is to compute the omega prime because it's just in algebra, and he looked for all the values of S to the 9, what is the best omega prime, and he found that the quotient omega prime of t is small only for its values. And then when we had 17 and 48, we say, oh, I have 8 points and I have 8. We need to take the 60, we give the answer, and this is what I explained. So I explained the situation for n equal to. I would like to go for any value of n. Instead of c squared, I see c to the n. So now I have a subset of c to the n, which is finite, and a positive integer t. The definition is the same. That your s is the smallest degree of the polynomial vanishing at each point of s within at least. So if I have 1 point omega t of s is just and the number of s element of s, and omega t of s is t, there is 1 point. It's one variable. In one variable, it's just cardinal of s, and in n variables for 1 point, we have t because we just take one variable. So this is also interesting. And if we have not more than 10 points, we just take a line, and if you have at most 10 points here, there is a line which passes the point. So this is for a Cartesian product, not that easy, but omega t of s is times the minimum of the factor of the s. It's a bit complicated. I know it because I gave a proof Saturday in my course in concept and my proof last month. So I got to it yesterday. This morning the student asked me some question and my proof is not yet complete. I have a full proof which uses integral formula, which is not elementary, but there should be an elementary, which I will try to write down. But it's true. Omega t of s is t times the minimum of the s. And the first notable case is 3 points in C squared, not in a line, but we have seen what it is. There are some cases which are not difficult. If you have hyperplanes, which means polynomials of degree 1, in general position, you can compute what is omega nt of s, and you have to consider how many intersections are there. And this is an example where you have n equal to 5 lines. You have a number of intersections which is 10, and it's easy to compute smallest d. So there are some special cases which are easy. The linear algebra which I defined before can be extended in n variables. The space of polynomials in n variables has dimension t% n. The number of tuples so that the sum is less than t minus 1, less than t, is t% minus 1 n. And therefore, if the number of elements of s multiplied by less, strictly less than t% n, omega t of s is greater than. So we have a upper bound, and upper bounds are not so good. So, for example, one of the bound is omega t less than t plus n minus 1 times s to the 1 over n. But you see that this upper bound is greater than the t times s 1 over n. So omega t over t is something which is larger than s 1 over n. Again, you have the additivity, and again, you have negative lemma because it's one input. And so the limit of omega t over t exists, and it's the infimum of omega t over t. And the main problem is with the bound. And this is the first result which I want to explain. Omega of s is positive and bounded by omega 1 of s. And omega of s is less than omega t over t. It is the infimum of this number. The capital omega of s is bounded by s power 1 over n. This is the bound which comes from the limit. I would like to explain how I got the first bound for omega of s, because to give a bound for the limits of the solarity control is something which is not easy. And this bound comes from transcendental model theory and from L2 estimates of Hilbert. So I do a little bit of the complex analysis several variables. Hilbert proved a theorem which is the approximation of what is called the plurisobariant function by the function which is the logarithm of an entire function. So what it proved is the following. In fact, these are improved by Bombieri. We have a plurisobariant function, Cn, which is not identical to minus c. There is a nonzero entire function f, but that this integral is bounded. So they look complicated, but what does it mean? We have to know what is a plurisobariant function. We just need to know an example, and the logarithm of the polynomial is a plurisobariant. So we just figure the logarithm of the modulus of the polynomial. So if we have for phi the logarithm of the modulus of the polynomial, which means that here we get 1 of the p of z, we can approximate 1 of the p of z by f of z squared. So we approximate by taking one type function. So the next estimate was improved a little bit by Skoda, and thanks to that, Skoda was able to improve by the one, and he got 1 over n omega 1 over n. I had a minus 2. And the difference is the exponential. The Skoda got minus n minus epsilon, while the Bombieri had minus 3n. You see the improvement of it. So I would like to explain the idea behind this proof to give a low bound. And it's really heuristic, but it explains the idea. So the idea is the first. You take a polynomial of degree omega t1 of s, with multiplicity t1. And the idea is to look at the function, the function at p of z, I will explain t2 over t1. This is not well defined because you have to take the root of some polynomial, but we can prove that this is not an entire function in general, but if we take the logarithm, it's a plurisobariant. But assume that it is an entire function. It's difficult from the estimate of the Hilbert, Bombieri, Skoda to deduce that it is a polynomial of degree t2 over t1 omega t1. And which vanishes on S with multiplicity t2, and this would give the bound for omega t1 with a sharp. This bound is not true, but using this estimate of we get the bound which is true, which is the bound for omega t1, and this bound enables one to have the bound for omega 1. So the bound that we obtain is omega t divided by t plus n minus 1. We should take n equal to a little bit weaker than what I found before. So there is an improvement which is going to come. The improvement comes from the conjecture of Chomsky. Chomsky conjecture that omega t over t is always omega 1 plus n minus 1 over n. And this was proved by Delahaye. So Delahaye improved the bound in the case n equal 2, and what he has is omega 1 plus 1, which is, again, not exactly the result which I obtained, but comes from the next picture. Another method, which is a method from projective geometry, was used by Eno and Fidei to prove that omega of s, that is omega t plus 1, divided by t plus n minus 1. And now if you take it down, this is the one which I did for n equal 2. So the result comes from several improvements of the bond. There is another result due to Jean-Pierre Lemani, who gave the generalization of the hypersurfaces formula. We got the new variant of the sharp lemma, and I will explain what is the sharp lemma. And then we got the new lemma, which again is the boundaries. Lemani had the conjecture, which is that omega of s is bounded by omega t plus n minus 1 over n minus 1. That in general this is not yet true. Hershowitz has another conjecture about the maximum of omega t of s over all finite set is n elements. And this conjecture is that this is as large as possible, and as large as possible means you look at what obtained from the linear algebra, and what you expect is that you cannot improve the linear algebra. The method of Hershowitz is implicit, that method always, and if you know the French would say les rois et les cueillasses, always and always, the ancient literature of the Greek, but it's I can tell you more about that. And there is some other short lemma due to Atari, where we got some partial result on this conjecture. Okay, so why was I interested in this problem with Nagata? I knew that it was connected with Nagata from curiosity, but I was interested in transcendental number theory. And one of the main results of transcendental number theory is a result due to Schneider and Young. Schneider gave a result in 1949, which was extremely complicated, but it was very general, and Young succeeded to make it very simple. And the theorem of Schneider and Young is just the theorem which is here. We have meromorphic functions. Two of them are algebraically independent. They do not go too far, they have a finite order. We have a number field, and we assume that each fi has a derivative, which is a polynomial f of fn. So these are differential equations, very simple. And then the set of w and c, which are not poles, because they are meromorphic, so that all the values are in k, is a finite. So this is a general result of the algebraic values of the meromorphic. And this result has a number of consequences. The first consequence is the theorem of Fermi-Lindemann, which states that if W is a non-zero complex number, one at least of the two numbers W is exponential W is constant. If W is algebraic, exponential W is constant. If exponential W is algebraic, then W, which is the logarithm of the algebraic number, is constant, provided W is non-zero. You deduce the transcendence of phi over phi from beta as a consequence of the Lindemann theorem, which follows from the Schneider-Young theorem. So this is one example. Another example is the solution of the Hilbert's seventh problem. I mentioned the 14th problem and the work of Nagata. And so Hilbert's seventh problem was to prove that if beta is an irrational number and W a non-zero complex number, one at least of the two numbers, exponential beta and exponential beta W, is constant. W is algebra, so it's algebra. One of them is constant. And this theorem has a number of consequences. The transcendence of e to the pi, 2 square root of 2, alpha to the beta, log alpha, all these numbers are transcendental. So these are two examples of applications of the Schneider-Young criterion to entire. But I took pleomorphic functions because there are some. So I will not give the proof of the corollaries because time is really difficult. But there is also some consequences in the Weierstrass elliptic functions, and it is an analog of the Hermite-Tiedemann theorem for Weierstrass functions. One of the theorems W and pure W is orthogonal. And for that, we have to look at the differential equations with the satisfied. So these are the examples of the transcendental machinery is construct an auxiliary function, which is the veritable principle in Sharp-Lemma, to find the point where the function is not zero, to give a Leblanc using Curie argument, and then to give a Leblanc using analytic argument. And this is in the step 4 that this number negative occurs. It occurs because of the Sharp's lemma. In one variable, the Sharp's lemma tells you that if you have an analytic function with at least n0, then fr is less than 3r, so the vector r to the n times fr. You see, this operand is better than the maximum modulus principle as soon as capital R represents 3r. So this operand considered and plays an essential role in the transcendental numbers. And the proof of the Schwarz lemma in one variable is very easy because we will use the fact that if alpha r is the root of f, the product of the 10 minus alpha r will divide f, and we use the maximum modulus principle for f and g. G is greater than g control r, and so the operand is very easy. But this is in one variable. If we want to deal with several variables, then there is a result of Schneider-Lange, which is very similar to what I have seen before. Instead of taking pleomorphic function C, we take pleomorphic functions in C to the n, and we take at least n plus 1. We assume that n plus 1 of these functions are independent. We have a number field. We have the differential equation, which are essentially the same. And we look at the basis of C to the n, and we say that the set of W, the set and O, does not contain the Cartesian product like this one. So, what does it mean that it does not contain the Cartesian product? It is related with a smaller degree of the polynomial. And in fact, Nagata, the same Nagata, attended the course of Lang in the 60s, where Lang explained this theorem. Nagata said to Lang, a better result is to say that this set is contained in algebraic hypersurface. It divides the. And so this was the conjecture, second conjecture of Nagata. And when the result which I just gave was useful to prove the transcendence of some numbers, like beta A and B, which is a beta function of the polynomial. This number is transcendental, and there are many other numbers in the transcendence of the Revenant number, which use the theorem of Schneider-Lange with the product. But the Schwarz lemma which was used was a Schwarz lemma only for a set which is a product, when which is time is a subset of Cn. And now the problem was to get the Schwarz lemma when we do not have the Cartesian product. And this is where the Bombieri came into the picture. The Schwarz lemma for Cartesian product is rather easy to prove. I give a reference here, but the suggestion of Nagata was that we should not use the Cartesian product. So we suggested that in the conclusion, the fact that F does not contain the Cartesian product, where each side should be replaced by the fact that S is contained in an algebraic version. This was his suggestion, and this was done by Bombieri in 1970. And so the theorem is the same, apart from the conclusion, the set S is contained in a natural system. So, and we go have a part argument which I use in the proof. Bombieri and Knight had a preliminary paper where they use something which is called the Bleuon measure. So they use the deep functions of complex analysis in several variables. But after that, there is a lot of tools which are used, in particular the L2 estimate of the number that the Bombieri used. So the natural question is the following. We have a subset of C to the n, the positive integer, and we ask the Schwarzschild several variables, which is another one for FR, with FR, and the number which would be smaller than 1, provided that we know that the analytic function vanishes multiplicity at each point of S. And the question is, what is the largest value of n? And the answer is given as follows. We use the Schwarzschild, which is conjectural, we know the n, that we want to put n as r as possible. We use it for non-zero polynomial, which vanishes on S. And from this above, we deduce that f has the degree of its n. So the largest value of n, the smallest degree of the polynomial, vanishing of S. And this is how omnidative of S occurs. And the Schwarzschild is omnidative of S. There is just an assumption that the R is sufficiently large. There exists a number R, so that for capital R greater than R, we have this. And this exponent omnidative of S is describable and will. There is a connection that some of you may understand with Seychelles constant. I prepared a few slides about that, but I will not explain them now. You can download my slides from my website, and I give a reference on the online lecture which I gave on the Nagata lecture and the constant of Seychelles, the Seychelles constant. And the multiple essential constant, but I prefer to say a few words about the commutative algebra. What I explained for points is a special case, the more general result, which meets with homogeneous ideals. There are anything here, zero characteristic. We take the ring of polynomials in n plus 1 variables, and we take homogeneous ideals. So you have a point in the projective plane, and you look at the homogeneous ideal generated by the polynomials which vanish at the point P. So to look at this homogeneous ideal, if you take the intersection of the IOP, this is exactly this ideal form which vanish on S at each point of S with multiplicity 1. So the name is the fact point ideal. And the smallest degree of such a polynomial in IOS is precisely omega 1. So we are now domain of commutative algebra, and there are many tools which can do. This is omega 1 of S, the smallest degree of the polynomial. In general, when you have a homogeneous polynomial, you can decompose it into homogeneous components, Jn, and this decomposition, omega of J is the minimum of n that Jn is not zero. This is called the initial degree. It's interesting that I used the letter omega, which is the last letter of the alphabet, and now in commutative algebra, they use the alpha, which is the first letter of the alphabet. That is like, so this is here it's omega of G, but very often leading term, the initial degree is called alpha. So if you have the ideal generated by the product of the omega of J to the T is T omega of J, which corresponds to the product of the polynomial. But you can define the symbolic power of the transcendental polynomial. You take the intersection of the P1, PNT, which means that you want the multiplicity T1, T at Pn, and you have the ideal forms which vanish because T. And so the initial degree of this polynomial precisely what you have. So we want to compare the ideal IFS to the T, so the classical power of manual, and the symbolic power of the same manual. We have one contained in the other, and the fact that we contain means that omega of S is less than T times omega of S. That's why I'm interested in the opposite direction. So I define symbolic powers for the flat point ideal. We can do it in general, and for that we have to use the primary decomposition of an ideal, and we take only the ideal where we take only the J which are contained in prime which are contained in I, just to say that the symbolic power exists in general for any homogeneous ideal. And we have this intersection, Jn is contained in J symbolic. And now the result which I explained before is that the symbolic power is contained in this intersection with the exponent which is n. This is the multiplicity nj. So the containment problem is to see when Jn is contained in J block. And I think my time is almost over, so I will just show you a few references on this question. And there are many people who have worked on that. In particular, Bocci and Harron have defined a number capital omega of J, which is infinite, and which is a generalization to ideals with K of x0 xn of the omega, which I defined before. And so this capital omega is defined now for any homogeneous idea. They prove that it exists and that it is bounded by this. This is the upper bound, which is what is not missing, is a low bound, and they have some low bound, which comes from the work of the hypersurfaces and also Foster and Hilbert. So they solve the containment problem, which is to show that the JCN is contained in JC. And this is a big project which I must say I do not understand yet the proof, but I want to study it. And there are two proofs, one by I. Nagata and Smith chooses multiplier ideals, and there is a book by Nagata on this topic. And the other method is by Foster and Hilbert, using continuous powers and type version, and they compare the symbolic power and the ordinary power. So it's a problem which is studied by many people, and especially Foster and Hilbert. And Bocci and Harron have produced something which is called the resultance, and it is related with the Castellano problem for regularity. And I would just say that this resultance has some connection with the Fermat theorem. And so we just end with something which involves number theory. So number theory comes back with the Fermat theorem, where there is something which is called evolution, which is related with the order. So many other people contribute to that. I think it's time. You have all these references on the